Now here's part 2 of the video for week 8 on alternating current circuits. It's an example. The example is exponential transients in an LRC circuit. And at the end of this video, there's a long kappa problem. There are instructions for a long kappa problem. So we have here an LRC circuit with a switch. And we'll say that for t less than or equal to 0, the switch is open and the capacitor is charged. It has charge plus Q0 on one plate, minus Q0 on the other plate. Then close the switch at time 0. What will happen? Well, now I have a continuous loop of conductor, and so current will flow. Current will flow through the resistor and the inductor. Now, of course, current can't flow through a capacitor because of the insulating layer, but it will change the charge on the capacitor. Energy will be converted by heating from field energy, which the system has when t is less than or equal to 0, has electric field energy in this capacitor, and be converted into random kinetic energies of the materials, well, mainly the material that the resistor is made of. So the resistor will dissipate energy, and gradually the charge on the capacitor will go to 0, and the current, when the capacitor is not charged, will just die out. So we'll have an exponential transient current. The current will flow for a while, but it'll gradually die out. This is a problem we've done before without the inductor. So we considered discharging a capacitor in an RC circuit. Well, things will be changed by the presence of the inductor because, as you know, the inductor can lead to oscillations. Okay, so for t greater than 0, the switch is closed, and now current will flow through the resistor and the inductor, and the charge on the capacitor will change. So I'll define Q of t as the charge on the upper plate, and minus Q of t will be the charge on the lower plate. And I'll say the current in the resistor flows to the right, and I'll say the current through the inductor flows downward. So I'm taking a positive current to meaning clockwise. Now, of course, it may be when I do the calculation, I'll find the current is negative. That means the current will be counterclockwise. In fact, because I have an LC circuit here, I can expect an alternating current. So I'll expect the alternating current. The current will sometimes be clockwise, sometimes counterclockwise. But because of the resistor, I should expect that the current will decay exponentially. Now the problem is to calculate Q of t, the charge on the capacitor, and I of t, the current. Well, the first step is to write down Kirchhoff's loop rule. So for t greater than or equal to 0, we have a continuous loop, and we can write down Kirchhoff's loop rule. The change in potential around the loop must be 0. So there are 3 places where the potential changes: across the capacitor, let's calculate the change in potential going around the loop in the clockwise direction. So the change in the capacitor potential is delta V sub C. And the capacitor charge is Q, plus Q and minus Q. So the change in the potential across the capacitor is Q divided by C. That's the definition of capacitance. Now we have the change in the potential across the resistor. And we're calculating the changes in potential around in the clockwise direction. And I'm assuming that the current is in the clockwise direction. Or I'm taking positive I to mean a current in the clockwise direction. So the change in the potential across the resistor is minus Ri. By Ohm's law, the current is the change in potential divided by the resistance. And now I have to figure out the sign. Well, I'm calculating the change in potential in this direction. If I assume that positive I goes to the right, then this would be the high potential side, driving current to this side, which is the low potential side. So the potential would go from a high value to a low value. The change in the potential would be negative. So delta V sub R is minus Ri. And finally, I have the change in potential across the inductor, which is just a solenoid. And, well, you remember self-inductance. The change in potential across an inductor is the self-inductance L times di dt. It's an effect of electromagnetic induction. As the current changes in time, there's a changing magnetic flux, and by electromagnetic induction, there's an EMF, which is just equal to the potential difference across the inductor. Now, the tricky thing is the sign. Delta V sub L is negative L di dt. And that is consistent with Lenz's law. Remember, Lenz's law says that electromagnetic induction opposes the change in the field, or the change in the flux, or the change in the current. So I want a potential difference that would cause a change in the current, that would oppose a change in the current. Now suppose di dt is positive, then I would want a potential difference which would create a current in the opposite direction. That's called the back EMF. So that means the change in potential is minus L di dt. So if di dt is positive, then delta V is negative. In other words, in the direction to drive current in the opposite direction from the change in current. All right, so the sum of these three terms is 0. So let me write that on the next slide. Kirchhoff's loop rule says Vc plus Vr plus Vl is 0. And Vc is Q over C, Vr is minus Ri, Vc is minus L di dt. So that's step 1. That's Kirchhoff's loop rule. All right, so one of the equations we need to solve this problem is Kirchhoff's loop rule. But we need more equations. We need a relation between Q, the charge on the conductor, on the capacitor, and I, the current. Now remember, we defined positive Q to be like this. This is plus Q. And the other plate is minus Q. And then we define the current this way to be I. So positive Q means a current coming in the clockwise direction out of the positive plate of the inductor, of the capacitor. Now I is the rate of change of the charge, so dq dt is minus I. You know, if the current is in this direction, then Q is decreasing. Positive charge is moving away from the upper plate, giving me a current to the right here. Well, that means that the charge, Q, is decreasing. And the rate of change of charge is equal to the current. But the rate of change of the charge is negative because Q is decreasing. So dq dt is minus I. Think of how much charge leaves this plate during a time dt. Well, on the one hand, it's I dt, and on the other hand, it's minus dq, the reduction in the charge on that plate. All right, now I can put that into I, and I can put di dt equals d squared q dt squared. Di dt will be the second derivative of q, or with this minus sign. Now let me divide the equation through by L. So this term will just become the second derivative of q, d squared q dt squared. And this term will be minus I is dq dt divided through by L, so r over L dq dt. And finally, this term will be, I divided through by L, so it'll be q over LC, or 1 over LCQ, and the sum of those three terms is 0. So there's the equation now as an equation for Q of t. It's a differential equation. It's a second order differential equation. So it's going to depend on two initial conditions. Q of 0 and dq dt of 0. At 0. For a second order differential equation, I need two initial conditions. Now I said that we're discharging the capacitor. So I'm going to take dq dt, I'm going to take q of 0 to be 0. I will impose that boundary condition. I'm not going to impose a boundary condition here. I'll write down a solution which corresponds to a particular value of dq dt, but I'm not going to worry about the general solution of the problem. I'll just write down one solution which corresponds to a particular value of the initial current. All right. Before I go ahead, I want to simplify the problem by introducing two parameters, omega 0 and tau. So this quantity will be omega 0 squared. So omega 0 is 1 over the square root of LC. You'll recognize that. That's the angular frequency for the LC circuit with R equals 0. So I'll call that omega 0. Corresponds to the case where R is 0. But anyway, it's just a definition of a parameter with units radians per second. I'm also going to introduce tau, which is 2L divided by R. And we're going to see later that tau will be the time constant for the exponential transients. But for now, I'm just introducing it as a parameter to simplify the equation. So now I'll have d squared q dt squared plus r over L. Now r over L is 2 over tau dq dt plus 1 over LC. 1 over LC is omega 0 squared times q is 0. All right, so now I'm going to work on this equation. I'm trying to find a function that satisfies this equation, a function of t. And the way I'm going to solve it is I'm going to guess the form of the function. I'm going to guess that it's an exponential. And then I'm going to find that, yeah, that gives me a solution. So I'm going to try this function e to the p times t, where p is a constant. So it's just an exponential function of time. Now I should expect that it's going to be a decreasing exponential, so p will turn out to be negative. In other words, it'll be a decaying solution. In exponential decay, the exponent is negative, so p will turn out to be negative, as we'll see. Now if I put that into the equation, when I take df dt, I get p e to the pt. And when I take the second derivative of f, I get p squared e to the pt. So I put in f here in each of these three terms for q. I will always have a factor e to the pt in all three terms. Because when you differentiate the exponential, you get the exponential back again times the derivative of the exponent by the chain rule. The derivative of the exponent is just a constant p. So those three exponential factors I'll just cancel out because the sum is 0. So the coefficient from d squared dt squared will just be p squared. And the coefficient from 2 over tau ddt will be 2 over tau p. And of course the coefficient from omega squared q will just be omega 0 squared. So this satisfies the equation if p squared plus 2 over tau p plus omega 0 squared is 0. In other words, the equation determines p. Not exactly. There are actually two solutions, because this is a quadratic equation. So I can write the two solutions to this quadratic equation. You see that p plus 1 over tau squared is equal to minus omega 0 squared plus 4 over tau squared. No, plus 1 over tau squared. So if I move this to the other side of the equation and take the square root, p plus 1 over tau will be the square root of 1 over tau squared minus omega 0 squared. But it could be either plus or minus the square root. So I actually have two solutions. This is a property of differential equations. The general solution for a second-order differential equation, well, it'll be a superposition of two solutions. And the two solutions are both exponentials, but with different values of p. So p could be minus 1 over tau plus or minus the square root of 1 over tau squared minus omega 0 squared. Either sign would solve this equation. So I've actually found two solutions. I've actually found an infinite number of solutions, because any linear combination of e to the p plus t plus e to the minus p plus e to the p minus t, any linear combination of the two exponentials, would also be a solution. So I have a whole family of solutions to the differential equation. What determines the actual solution for the problem I'm interested in? The answer is the initial conditions. Well, let's go on here with this general solution, or rather two general solutions. And let's consider a special case. We'll consider the special case, which is called underdamped oscillations. In other words, the damping is small, so the LC characteristic of the problem is important. Well, you know, if R were 0, you would just have oscillations. You just have harmonic oscillations. We've done that problem before. So for R small, we should expect to see oscillatory motion. Now let's see what we get. And the relevant scale is the square root of 4L over C. So suppose R is less than the square root of 4L over C. That's the same as omega 0 greater than 1 over tau. So tau is sort of a measure of the decay. Omega 0 is a measure of the oscillations. Well, omega 0 is large compared to 1 over tau. They both have units of 1 over time. Means that the oscillations are important and the decay occurs slowly. That's what we call underdamped oscillations. Now, why are these two inequalities the same? Well, remember, omega 0 was 1 over the square root of LC, and tau was 2L over R. So this condition says that 1 over tau, which will be R divided by 2L, is less than 1 over the square root of LC. So in other words, R is less than 2L times 1 over the square root of LC. Is that clear? If I put in here 2L over the square root of LC, then the 2L's will cancel. I'll just get tau is equal to 1 over omega 0. So the kind of dividing point between overdamped oscillations and underdamped oscillations is at R is the square root of 4L over C. Let's see. 1 over tau would be R over 2L. So R is less than 2L omega 0. And omega 0 is 1 over the square root of LC. So you see I have the square root of 4L over C. So in other words, I want to consider the solutions where the parameters have this property. Omega 0 is bigger than 1 over tau. Now something funny happens here. Because if omega 0 is greater than 1 over tau, then I have the square root of a negative number. Square root of a negative number is an imaginary number. So P will be minus 1 over tau plus or minus I omega, where I is the square root of minus 1. So I here doesn't mean current. Don't confuse this I with the letter I was using for current. This I is the square root of minus 1. Sometimes engineers call the square root of minus 1 J. But usually mathematicians and physicists call the square root of minus 1 I. So you see this is minus 1, omega 0 squared minus tau squared. The square root of minus 1 is the I. And then omega is the square root of omega 0 squared minus 1 over tau squared. So omega is the square root of omega 0 squared minus 1 over tau squared. It's approximately equal to the natural frequency of the LC circuit, which would be omega 0. But in fact, it's a little smaller by an amount that depends on the resistance. All right, so my solution to this equation is e to the pt, that's e to the minus t over tau, and then e to the plus or minus I omega t. Now, how can that be the charge on a capacitor? The charge on a capacitor has to be a real number. It's some number of coulombs. It can't be an imaginary number. So there's something mathematical going on here. I have to have something which is real. And if you've studied complex numbers, you'll know what's going on here is called Euler's equation. All right, so here was my solution. E to the minus t over tau, e to the plus or minus I omega t. And here's Euler's formula, which you should know from calculus. E to the plus or minus I theta is cosine theta plus or minus I sine theta. A complex exponential is equivalent to a combination of trigonometric functions. So I could replace this e to the plus or minus I omega t by cosine omega t, or by sine omega t, or by some linear combination of cosine omega t plus sine omega t. Because the e to the plus I omega t is a solution, the e to the minus I omega t is a solution, the cosine omega t is a solution, the sine omega t is a solution. Any combination of those, any linear superposition of those is also a superposition, is also a solution. So to make it simple, let's consider the initial condition Q of 0 equals Q0. And let's write the solution Q0 e to the minus t over tau cosine omega tau. That's not the most general solution. It is a solution of the differential equation, and it does satisfy this initial condition, because if I set t equals 0, the cosine of 0 is 1, and the exponential of 0 is 1. So at t equals 0, I'd have q of 0 is just q0. But I could also write a term with sine omega t. That wouldn't spoil the initial condition. I could write any combination with sine omega t. That would allow me to also satisfy an initial condition on the current. But I'm not going to worry about that. Instead, I'm just going to consider the simplest case, where the solution goes like cosine omega tau. It satisfies this initial condition. It has a particular value of I. It corresponds to a certain value of I at 0. It's not necessarily 0, it's not necessarily 1, well, remember I is minus dq dt. Now if I differentiate this term, I get sine omega t, but then when I set t equals 0, that'll be 0. When I differentiate this term, I'll get 1 over tau. So this solution for the charge corresponds to this initial condition on the current. It's Q0 divided by tau. And that'll be good enough for my purposes, just to see how the functions behave in time. It's a particular solution. I of t would be minus dq dt, so here I can have the derivative of the exponential. That'll give me the factor 1 over tau cosine omega t. Or I could have the derivative of the cosine. That'll give me omega times the sine, or actually minus omega times the sine. But remember, this minus sign will make it a plus, omega sine omega t. So here would be the current as a function of time. And in particular, if I set time equal to 0, sine omega t would be 0, cosine would be 1, exponential will be 0, it would just be Q0 over tau. So it corresponds to a particular value of the initial current, which I'm not too interested in. Now what you have here is an alternating function because of the cosine factor and an exponentially decreasing function because of the exponential factor. And similarly for I, you have an oscillating factor from the trigonometric functions and an exponentially decreasing factor from the exponential. So what we have here are called exponential transients. When t goes to infinity, q will just go to 0, and I will go to 0. So that's the kind of steady state. After I close the switch, after a long time, the capacitor will be no charge, and the current will go to 0. So both of these functions will approach 0 in the steady state. But starting from the initial condition, they approach that steady state solution exponentially. Those are called the exponential transients. And I can just plot this function. I mean, let's take the value omega 0 of 1, the value tau is 4. Omega, remember, was the square root of omega 0 squared. That'd be 1 minus 1 over tau squared. That'd be minus 1 over 16. So omega is a little bit less than the natural frequency without resistance. It's 0.968. This would correspond to resistance 0.5 ohms, inductance 1 Henry, capacitance 1 farad. So just some kind of generic values for the constants. Then I have these functions, and I can just plot those functions. The red graph here, the red curve here, is q as a function of t. I guess I also took q0 to be 1. Anyway, q will start at q0. So it starts at q0. I starts at some value, doesn't really matter. I is the blue curve. Q, you see, eventually decays to 0. In other words, the capacitor discharges. I goes along with the slope or the derivative of the curve of Q. So where Q, the slope of Q is 0, I is 0. You know, at where Q is at a maximum or a minimum, the slope is 0. So you see you have these exponentially damped oscillations. All right, so that's the analysis of that problem. And now I want to give you a problem to do yourself, which is a ln kappa exercise. So here's the ln kappa problem. I'll give you values for LRC and Q0. Not these values, but some randomly selected values for LRC and Q0. And I'll ask you to calculate the field energies. This tells you the charge and the current. Well, now calculate the field energies. You remember for U sub C, the field energy in the capacitor is Q squared over 2C. We learned that some time ago when we talked about capacitors. And U sub L, the magnetic field energy, the energy in the inductor, the energy associated with the magnetic field in the solenoid, is 1/2 Li squared. Which again we learned back in chapter 29. So I'll ask you to calculate the field energies. Now, as you see, the energy is tending to 0. But of course, energy is always conserved. So that energy has to go someplace. I mean, it started out with this electric field energy in the capacitor. After a long time, there's no energy left. Where did that energy go? Well, it went to heating up the material in the resistor. And so the third quantity to calculate is the power dissipated in the resistor, P sub R. And you remember the power dissipated in resistance is I squared R. All right, so this gives you the problem in week number 8 on ln kappa.